Hi, everyone, and thanks for the introduction. I'm excited to be here. I wish it was in person. Talking to my screen is getting a little old. But anyway, let's make the most of it. So this is a talk about rapid, frequent, reliable, and sustainable delivery of software and why it's important, the impact that that has on architecture. Or in other words, what are the architectural requirements for that? And then I'm going to compare and contrast sort of the two key architectural patterns, the monolithic architecture and the microservice architecture. There's so much debate today, especially on Twitter, about, yes, monoliths are the future, no, microservices are the future, and so on. So I'm hoping to clarify that. So a little bit about me, if you don't know me, done a number of things over the years. I did Lisp back in the late 80s, early 90s, ended up in the Java world, wrote the book Pojos in Action, created the original Cloud Foundry. And then for the past, 8 years now, we've been pretty much focused on the microservice architecture, helping organizations adopt microservices successfully through consulting and training. And yes, so microservices.io and the book Microservices Patterns. So that's me. I just sort of think about software architecture for most of the time. So here's my talk. So let's just get into this. So I want to begin about what do you need from your software architecture in order to support rapid, frequent, reliable, and sustainable delivery of software? And what is that anyway? And why is it important? So I like to explain it this way. There's like two trends, right? The first trend is that software is eating the world, as Mark Andreessen said back in 2011. Products and services are increasingly powered or enabled by software. At the same time, the world is a very dynamic or volatile, uncertain, complex, and ambiguous, and just kind of crazy place, right? From a sort of more mundane level, traditional or companies are facing threats from new startups, such as brick and mortar banks facing competition from digital startups as a result of deregulation. And then on top of that, we have COVID, right, which has been the ultimate disruptor. In addition to all of the chaos it's created around the world, I think it's had a big impact on IT. So as a result of this unpredictable nature of the world, businesses need to actually be much more nimble, agile, and innovate at a faster rate in order to be successful. And given that software is powering everything, we in IT need to deliver software rapidly, frequently, reliably, and sustainably. And you can actually quantify that, at least the rapid part. The goal today is, for reasons I'll get into, to deploy multiple times a day, ideally once per developer per day. And the lead time, the time from commit to deploy into production, should be under 15 minutes, right? Quite a dramatic shift from the traditional sort of quarterly, weekly, or whatever releases you use. And the way you accomplish that is with what I call the success triangle. You need the right architect, you need the right process, which is basically DevOps as defined by the DevOps Handbook. It's a set of principles and practices for delivering software rapidly, frequently, and reliably. You need the right organization structure, which is a network of small, loosely coupled, empowered product teams. And the Team Topologies book is an excellent guide to that. And you need an architecture that actually enables those two things. And I'm going to talk more about that in a minute. And then another issue you have to consider is that applications that we write, if they're successful, they live for a long time, 10 or 20 years or even longer. Yet at the same time, technology changes. And it's really important that the technology that an application uses remains current, which is a huge challenge. And once again, that actually has requirements on architecture. So what is this architecture thing that we talk about, right? So here's a classic definition of that. It's a set of structures needed to reason about the system which comprises of software elements and the relations or relationships between them and the properties of those elements and the relations. So, short answer to that is a bunch of boxes and lines, but those boxes and lines have very specific meanings. And this directly has impact on this whole monolithic versus microservice architecture. And I'll get into that more. Why is it important? Well, basically, architecture enables an application to satisfy its non-functional requirements or software quality attributes. And usually organizations sort of focus on the ones that sort of have direct impact to the user, namely things like performance and availability and scalability and so on. So the runtime category, but there's also these development time requirements around maintainability and testability. And unsurprisingly, it's those development time attributes that actually relate very directly to the topic that I'm discussing here. So the book Accelerate, which is a must-read book, surveys organizations, and it's found that developers in high-performing organizations generally agree or strongly agree with the statements on this slide. Like, I can complete my work without communicating with people outside of my team. I can test without requiring an integrated environment. I can change things without requiring others to make changes to support my changes. And if I make my changes, it doesn't impact other teams. And I can deploy my application independently. That actually has strong architectural implications. So, number one, if you apply Conway's law, if you have a loosely coupled organization, you need to have a loosely coupled architecture. The fact that I can make changes without impacting other people requires a modular architecture that encapsulates design decisions. The fact that I can test locally without requiring an environment, I could generally classify that as a testability requirement. And then the fact that I can deploy or release independently, you could say requires an architecture that's deployable. So we've got these four requirements on our architecture. And then also the fact that we want to be able to develop sustainably, which means that we need to be able to upgrade the technology stack. And the best way to do that is just incrementally one part of the application at a time, as opposed to a difficult to schedule big bang upgrade project. That's another property of our architecture, where a module's API encapsulates the technology stack. So if we were to sum it all up, there's a whole bunch of these sort of development time architectural requirements. We need testability, deployability, maintainability. We need loose coupling and modularity, and we also need evolvability. So key attributes in order to deliver software rapidly, frequently, reliably, and sustainably. So let's look at the architectures that enable that. So I want to talk about sort of the process for defining an architecture. So I like to use the following process. It all starts with the requirements, right? Whether that's like user stories, as well as the non-functional requirements. Perhaps you've done event storming to understand your domain as well. First step, I like to distill the requirements down into a set of system operations which model the requests in a sense that the system must handle. So if this was like an e-commerce system, you can create customers, you can create orders, you can find order history, and so on. So that kind of captured is sort of a distillation of the application's functional requirements. The second step is really to apply concepts from domain-driven design and then model each chunk of business functionality as a subdomain. And you could also call it a bounded context. There's some sort of fuzzy terminology around those words, but it's an implementable sort of object-oriented model of a chunk of business functionality. It's team-sized. It's owned by a particular team. So the customer team works on customer management. The order team works on order management. And they have to be loosely coupled. And there's actually a few other design criteria as well. You know, if this was a Java application, these are our packages and classes, right? Sort of the logical development developer view of the software that you're building. So, but it needs to run, it needs to be executable. So the next step is to figure out how to group those subdomains into components. And a component is a deployable or an executable, like a WAR file or an executable jar file. And so each component is a collection of subdomains. So it ends up being a partitioning problem. So if we think about it, right, we've got customer management and order management. Do they go together in the same component, or should they go in separate components? And I like to use a couple of metaphors from astrophysics to capture the idea of the various concerns that you have to think about. So the first metaphor is dark energy. It's an anti-gravity that's accelerating the expansion of the universe. It's a metaphor for repulsive forces that encourage the decomposition of a system into separate components. You can think of it as forces that are that are pushing the customer and order subdomain apart. And that involves requirements for like team size services, fast deployment pipelines, and so on. So that's one metaphor. There are a whole bunch of forces that encourage you to decompose your system into separate components or services. Yet at the same time, there are attractive forces. And the metaphor that I like to use for attractive forces is dark matter. That's an invisible matter that you can observe through its gravitational effects on stars and gravity. So you can think of that as a set of forces that resist decomposition. They're generated by system operations that span subdomains. So if we have an operation that spans the customer and order subdomain, there are these attractive forces that encourage you to package them together into the same service. So for example, the desire to have ACID transactions instead of eventual consistency, the desire to minimize runtime coupling. So we've got this dark energy, dark matter metaphors for the conflicting forces. So we look at the repulsive forces in a bit more detail, right? They're encouraging you to decompose. So that includes simple components, right? Generally, we like the parts of our system to be as simple as possible. We want teams that own those components to work autonomously. We want fast deployment. We need to support multiple technology stacks, which is a strong technical requirement to put your Python code in a different executable than your Java code, for example. Sometimes if components have different scaling requirements, we need to deploy them separately. And then there's sort of a general requirement to segregate subdomains by type, which might be whether they're regulated. You know, there's sort of if you're in a medical domain, there's strict requirements on how you develop and test and deploy your software. And you'd want to have the regulated components separate from the unregulated components. There are also reasons to separate your core domain from your supporting subdomains, for example. And then likewise, you want to separate highly available components from components that are less mission critical. So there's a whole bunch of reasons to split or decompose. Yet at the same time, system operations that span those subdomains create these attractive forces. So as I said, right, it's better to have ACID transactions as opposed to eventual consistency. You want to minimize runtime coupling. You want efficient inter-service communication. You don't want lots of round trips resulting in high latency or transferring large data sets across the network. And then you also need to minimize design time coupling between different components or services. So for these reasons, these forces resist decomposition. And so the job of an architect when figuring out how to partition a system into subdomains is to resolve these conflicting forces, minimize the repulsive forces within a service or component, and minimize the attractive forces between different services. So interestingly, this, I thought about dark energy, dark matter as a way to kind of design a microservice architecture, but it turns out that it sort of also includes the monolithic architecture as well. So, we think of it, we can just view the monolithic architecture as a system that consists of a single service or the application. So it fully resolves the attractive forces because there's only one component, right? But it potentially neglects the repulsive forces. And then on the other end of the spectrum, you've got the microservice architecture, right? That's sort of oriented around resolving the repulsive forces, but it potentially neglects the attractive forces because through decomposition, you can create runtime coupling and design time coupling and so on between your services. So there's sort of these interesting kind of comparisons between the two. So let's have a quick look at the monolithic architecture. And I want to say this over and over again. The monolithic architecture is not an anti-pattern. It's a perfectly good choice for a wide range of applications. It should just be one of the architectural patterns, in your toolbox as an architect. So it's quite funny. I look back over the years, say at various startups I've been involved with, and we began development of multi-year project, which turned out to be a monolithic application simply by making a directory and typing code in, right? And then if you were super cool, you could go to Spring Initializer and auto-generate a skeleton application or use JHipster or something like that. So here's an example of a monolithic architecture sort of built in this classic style. It's sort of it's oriented around technical layers, right? So classic sort of 3-tier. We've got a web sub-project that's got web-related functionality for the customer subdomain and the order subdomain. Likewise, there's a domain layer that's got the business logic for each of those subdomains, and then there's a persistence layer that's got the persistence logic for each of those subdomains. So it's sort of, just classic monolithic architecture. And I feel like I've built many over the years. And then, of course, there's a single deployment pipeline that builds, tests, and deploys the application into production. So simple, everyday monolith. Now, how does that kind of resolve the forces, right? And it's an interesting mixture. So it fully resolves the attractive forces because there's simply one component, right? The attractive forces only exist between multiple components. So there's no problem there. And that's actually part of the appeal of the monolithic architecture. It makes things rather simple. But if we start looking at the repulsive forces, is it a simple application? Well, that depends on the size. The monolith starts off simple, but typically grows over time, and I'll talk more about that. So that over time, it becomes increasingly a problem. Do you have team autonomy? Can people work easily on different parts of the application? So. And as the application grows in complexity, that becomes more of a problem. Is the deployment pipeline fast? Certainly in the beginning, but once again, that's proportional to the size of the application. Can it support multiple technology stacks? No. Or at least as far as it would be really challenging to have, Java and Rust inside the same monolith, right? It's sort of like a kind of, if it doesn't run on the JVM, you sort of have a problem. Can it scale in a cost-effective fashion? And there the answer is generally yes. Either the monolith, you just run multiple instances of the monolith behind a load balancer and it just scales. But if you have different parts, different functions with different scaling requirements, you could deploy the same monolith in different roles on different hardware and scale in a cost-effective fashion. Does it let you deploy regulated software separately from unregulated software? No. Does it really let you deploy highly available mission-critical software separately from less critical components? No. So there's sort of the good, the bad, and then there's kind of the ugly with this architecture. And then the other sort of issue you have to consider is that over time, some of those problems get worse, right? You know, many companies or many applications have started off with a very small team, you know, just 10 handful of developers. But, you know, when you're successful, the team grows in size, right? And, you know, steadily the application gets bigger and bigger and bigger. You know, I don't know if there's a actual accurate metric, but you could say every day a developer adds 50 to 100 lines of code, right? So over a long time period, you will end up with a massive application. You know, I've worked with clients where the actual WAR file is measured in gigabytes. At least one client I worked with, their whole business, hugely successful, was a collection of multi-gigabyte monolithic applications. And then, so you end up operating at very large scale, which leads to a whole bunch of problems. Even something as simple as just cloning the repository and then making changes and committing the changes can be a challenge, right? You know, doing a git clone of a large repository is challenging. If you sort of want to run the pre-commit test for a large application, even though they execute very quickly for a large application, that can still take a while. And then also by the time they finish running and you do a git push, someone else might have pushed in the meantime. You know, once again, you're thinking of a context where every day each developer is committing and pushing their changes at least once. So you've got a whole bunch of just problems with the basic workflow here. I mean, you can solve that by throwing some technology at it. You can use partial or shallow clones. You could use a merge queue to automate the merging of or testing and merging of PRs. But you know, development at scale is sort of in many ways a research topic. And then also, it can be challenging to meet the 15-minute lead time goal for your application, you know, especially if you're running on a stateless, ephemeral, continuous integration as a service system, right? Downloading the dependencies can take quite a while. I mean, it's quite ironic, even with a Node, you think of Node.js as being super lightweight, but doing an npm install from scratch can still take a few minutes, right? And as the application grows, it has more dependencies. Compiling it, that's usually not a bottleneck, but a huge bottleneck is actually running the tests. You know, it could take potentially hours to test a large, complex application. And so the lead time is very proportional to the application size. And, you know, it doesn't take, you know, it can be actually quite difficult to achieve a short 15-minute lead time once for a large application. I mean, you can certainly throw technology at the problem, right? And use a sort of mixture of some sort of basic build technologies like incremental builds and caching downloaded dependencies between builds. You can use some slightly more advanced techniques like distributed build cache. And then you can also parallelize your build. You know, for instance, there are build tools that can run on a cluster of machines. Those, I think, say Gradle, I think that just runs on it. You can scale it vertically with multiple threads on a single machine. So there are real challenges, right? And at the same time, the teams aren't really able to deploy their changes. There's still coordination. And then we also don't want to end up investing sort of brain power in our build system, right? Our brain power should be focused on developing features for the customer, not implementing an at-scale build system. So are there a few things we can do? Now, interestingly, if you look at this architecture, this is the slide from earlier, there's a bunch of choices we made. We had one Git repository. Inside that Git repository, there was one Gradle project. And then the orientation of the modules was actually technical layering. So those are a particular set of choices, but there are other choices. We could have many repositories. We could have many Gradle projects. And we could also, instead of horizontal technical layering, we could have vertical slices. So there's actually 3 variables, and each one has 2 different values. So in a sense, there's actually 7 other possibilities that we haven't explored. And I'm not going to talk about all of them. I'm just going to pick a couple. So one of them is actually having a modular monolith, right? Where instead of horizontal technical layers, it's domain oriented, or in other words, there are vertical slices. So the orientation is around subdomains, and then inside each subdomain are the technical layers. Yes, there's still a single large repository, so there are issues with that still, and there's a single deployment pipeline that can be slow and complicated, but there are some benefits, right? It's organized around vertical slices. That actually improves ownership. It's clear which team's responsible for which subdirectory hierarchy inside the actual project. And it's also more modular as well, right? Before, everything was all sort of tangled together. I mean, there were packages, but there wasn't this usual kind of coarse-grained modularity. Whereas in this architecture, there is, for example, a customer API module that sort of defines a sort of coarse-grained sort of service-style API for the customer subdomain. And so the actual order module doesn't depend upon customer. It actually depends upon the customer API module. And this actually promotes loose coupling. Just the other day, I talked with someone who actually used protocol buffers to actually define the module APIs in their system. So this has a whole, in addition to improving modularity, it actually accelerates builds as well, because API modules tend to be much more stable. So if order depends upon customer API instead of customer, we never need to rebuild it when we're just changing the customer implementation. Hopefully the tests catch everything, right? And we can actually test the order module using mocks for the customer API module, which is actually faster. So it's much more modular. And then there's sort of a bigger issue about how modular do you want to go? So one aspect there is transaction boundaries. We could stick with the usual transaction per request. That gives us sort of simple ACID transactions and efficient data access. But it does mean that our modules are tightly coupled through transaction boundaries, which makes it harder to migrate to services. So we could actually have a much more loosely coupled architecture by just limiting the scope of a transaction to individual modules. The trouble is that's actually much more complex, because now we've got eventual consistency inside our monolith. And then another thing to consider is, well, the interaction or communication patterns between our modules. It's all in, say, Java. So, well, we'd expect just to use method calls, right? That take parameters and return some values, and the caller waits for the method to return or throw an exception. So that's actually, in a sense, that's sort of tight runtime coupling, especially if we were to translate our modules into services. And so if we kind of think that's in our future, you might want to use sort of an asynchronous style of communication, events or async request response or one-way commands inside the monolithic application, because that creates the possibility of refactoring to microservices later. Makes it easier. But it's like, should you? Right? Should you have a transaction per module, which requires more complex eventual consistency? Should you use asynchronous intermodule communication, which is more complex? Because in many ways, what you're doing is you're incurring many of the costs and complexities of the microservice architecture without some of its benefits. And namely, like independent deployability and so on. So, the phrase "you ain't gonna need it" comes to mind. And so it's questionable exactly how modular you want to make things. Then another variation on this pattern is to actually have multiple repos, repositories. That actually sort of solves the scaling the repository problem, makes pushing changes a lot easier. There's clear ownership, teams own particular repositories. Each deployment pipeline at the module level is simpler and faster. You do need to think about how to enforce a consistent set of dependencies across all of these modules. Probably need to use a Maven bomb or Gradle platform project, something like that. But then you also have this issue that ultimately you have to assemble these modules into an application, and that can involve some testing, and that could be a bottleneck. Because one of the key challenges you have is you can test the customer module and that verify it works. You can test the order module, verify it works, but can you compose them together? Do they have a compatible set of dependencies? Do their Spring Bean names conflict? There's a whole set of potential problems that you can encounter that make it that require extensive testing of the assembled application, which is potentially slow and complex. So, some interesting sort of variations of the monolithic architecture. And kind of, I guess in summary, right? So some of the downsides of the monolith can sort of be mitigated by modularizing it and throwing technology at it, which actually enables this architectural pattern to be used for larger applications. But there's always this ever-present risk that you will actually outgrow your monolithic architecture. And then on top of that, there are some inherent limitations of the monolithic architecture, like the inability to support multiple technology stacks, which not only is it like Java and Python, but there's an issue around incremental upgrades as well. So there are real issues around sustainability. So that then leads to the microservice architecture, right? And that's an application that consists of multiple components or executables. Each one has its own repository and deployment pipeline and a path to production. So there's no longer this application level, or you try and avoid having an application level deployment pipeline. Each service, right, it's a collection of subdomains. It has an API that has operations. It publishes events. It can collaborate with other services by invoking their operations and consuming their events. Usually each subdomain is sort of packaged and deployed inside a single service. But there are situations where, say, you have a utility subdomain like money, which basically is deployed as a library inside multiple services. That's okay if different services can use different versions of the library. If they all have to use the same version of the library, then you've basically created a distributed monolith at that point. In this architecture, there are a few different collaboration patterns. A command that spans multiple services needs to be implemented using a mixture of the Saga pattern and the CQRS pattern, which replicates data. Queries that span multiple services need to be implemented using the API composition pattern or the CQRS pattern. So there's some of these sort of kind of interesting, more complex patterns that you have to use. So if we look at how this rates in terms of resolving forces, there's a whole bunch of potential benefits because it can resolve the repulsive forces, but at the same time, there's the risk of not resolving the attractive forces and, say, having, you've got eventual consistency and tight runtime coupling and tight design time coupling. So, and so if you like microservices, you think about the resolving the repulsive forces. If you dislike attractive forces, and if you dislike microservices, you focus on the unresolved attractive forces. But it's really the job of the architect to group the subdomains, actually break the system up into services in a way that maximizes the benefits and minimizes the drawbacks. And that's challenging because these attractive and repulsive forces conflict. So here's a really simple example, right? We've got 3 different subdomains, and there's sort of repulsive forces encouraging decomposition. Yet at the same time, there are attractive forces that are resisting decomposition that are generated by these system operations like find order, which spans order management and fulfillment, and createOrder that spans all 3 subdomains. So there's numerous ways of grouping these subdomains into services. And I actually organized them from left to right. And on the left, obviously, there's a monolith, and on the right is a fine-grained decomposition. And in between are various other permutations. And they vary in terms of how well they resolve the repulsive forces. Monolith, not so much. 3 separate services, very well. But then conflicting with that are these attractive forces, right? Which is sort of a function of how complex the implementation of the createOrder and findOrder operation are, right? So the monolith simplifies everything, whereas the fine-grained decomposition makes things complicated. And it's quite a common anti-pattern in the when using microservices is to have a very fine-grained architecture, but that results in these unresolved attractive forces. So you can end up with a distributed monolith, which is sort of brittle because of tight, long chains of synchronous calls, runtime coupling, in other words. And development is unproductive because of tight design time coupling across all of these services. And so as an architect, you have to balance these forces and find the right kind of decomposition that does its best at satisfying the repulsive forces, like enabling team autonomy, while at the same time sort of simplifying or optimizing the implementation of some of the operations. So in this example, I decided it was like, we want to split up as much as possible, except that there was real value in grouping together order management and customer management, because it dramatically simplified the implementation of the create order operation. Once the order had been created and the customer's credit had been reserved, all it needs to do is send a notification to the fulfillment service, which is a very, very simple saga. So, and given that I'm going to argue that that's a really key operation, there's real value that's the one you want to optimize. Yet at the same time, the find order query spans multiple services, so it needs to be implemented using API composition. So this was sort of like a worthwhile trade-off, right? The key operation is simple. The not so important operation is a bit more complex. Yes, the teams are not fully autonomous, but it sort of ends up being a worthwhile trade-off. So those are the kinds of decisions that you need to make when designing a microservice architecture. But of course, there are just these inherent problems with building a distributed system. There will be operations that are implemented using eventual consistency, right, or base. So whereas ACID is really simple, base is a much more complex transaction model. You need compensating transactions. You need to use sagas, which are not ACID, they're actually ACD, and so they don't have the isolation property, which can lead to data anomalies, which you then have to analyze your design for, and then select countermeasures to prevent. So it's kind of complicated. APIs are much more complicated, right? In your Java monolith, an API is a Java interface. A module call is simply a method call. The compiler checks it, and things either work or they don't. In the sense, you just sort of have complete or total failure. And you contrast that with a distributed system where your APIs are defined using like not your programming language, like Swagger or protocol buffers or JSON schema. You have to use libraries for communication. You don't actually have compile time checking of API compatibility. So you have to use more complex techniques like consumer-driven contract tests to prevent breaking changes. And then the failure modes are much more complex. If the order service invokes the customer service, you have partial failure or you have high latency. And then testing is another really interesting issue. It's common to have acceptance tests that span multiple services, which require these slow, brittle, complex end-to-end tests. And that sort of ends up being a real barrier to achieving minimal lead time and fast recovery from failure. So you have to encourage the QA organization to refactor the acceptance test into service level acceptance tests, which is kind of a different way of thinking about, testing. You could run traditional acceptance tests actually in your production environment. That's one good place to actually to do proper end-to-end testing. And then you can also integrate that in with Canary deployments, where you deploy the new version side by side, and with the old version, test it, incrementally move traffic over while monitoring it. And if there's a failure, roll back. Otherwise, you just move all of the traffic to the new version and then ultimately undeploy the old version. So that's another place that sort of end-to-end acceptance tests can be used. So, gosh, that's my talk pretty much. So, and I talked about a whole bunch of things. I mean, obviously the key message, right, is that there are two trends, like software is eating the world and the world is becoming this crazy place that directly results in IT needing to deliver software rapidly, frequently, and reliably. There's also the sustainability trend that then leads to having to needing a loosely coupled, modular, testable, deployable architecture, which sometimes can be a monolith, but sometimes needs to be a modular monolith. But once you get to a certain level of scale, it often needs to be a microservice architecture. And this architecting is something that we need to do constantly through the lifetime of your application. You often need to evolve the architecture, perhaps from a monolith to a microservice architecture. And you're just sort of constantly picking the patterns that resolve the forces that are generated by dark matter and dark energy. So that's my talk. Thank you for listening, and I hope that you found it useful.
Thank you, Chris. We do have a couple of questions, so let's start with the first. What do you think about a mix between very small services with some bigger monoliths?
I guess the short answer there is, yeah, sure. I mean, I would not say, what I would say is you've got a mixture of services that vary in size. Right? Like if you think, specifically, if you think about the definition of a monolithic architecture is where you have a single deployable unit, right? And then the alternative is sort of the microservice architecture where you have multiple deployable units. The architecture you're describing here is basically a collection of services with varying sizes.
All right, thank you. Let's go into the next. This is more of a comment, but let's hear your thoughts. Regarding segregated deployment in the monolith, you could deploy multiple binary modules like jars or assemblies independently. What do you think?
Yeah, it sort of depends on what you specifically mean by that. But I mean, I guess you could say I suppose one specific technology could be OSGI, right? Anyone remember that? In a sense, for monolithic architectures that let you deploy things deploy modules independently. So yeah, that sort of represents a certain set of trade-offs. I mean, there are issues around particular failure modes or the ability or lack of isolation between modules, so that they're all running in the same process, sharing the same CPU, the same heap, and so they can conflict with one another. I guess they can have, like with OSGI, they could have separate class paths, and so that's sort of kind of an interesting form of modularity that's worth considering.
All right, thanks. I've got a couple more, so let's keep going. What do you think using gRPC protocol between internal microservices?
Yeah, sure. I mean, it's sort of, I suppose it depends on precisely what parts of gRPC, but I sort of put gRPC in the synchronous communication category, though I mean it also has a streaming capability as well. So then, so the order service could use gRPC to invoke the customer service, but then in essence, you've got runtime coupling, which is the same flavor of runtime coupling as if it was REST, right? And so, yeah, sometimes that works. Sometimes the reduced availability and the increased latency that results from runtime coupling is not acceptable.
Great. Let's go on. How do you usually approach automated testing in microservices to keep the dependencies low, but to have the confidence that nothing of substance broke? For example, complex sagas.
Yeah. Well, I mean, they're sort of related as part of that. I mean, consumer-driven contract tests are really important, right? I mean, if that's sort of for API, enforcing API compatibility, and that's part of sagas, right? I guess the other part of it is I would design your system in a way to try and avoid the complexity so that you actually construct. So kind of hidden in one of the hidden messages in my presentation is your system should be comprised of simple components interacting in simple ways. And I think part of that is when you write automated tests for a component, you should be confident, and those tests pass, you should be confident that your component works as expected. So it sort of ends up being you architect for testability, in other words.
All right. So we have 2 more questions. Shall Lispers ever inherit the earth? And if that happens, what will the architectural patterns look like then? How does, in your mind, for example, closure enable different thinking in architectures?
Well, 2 points. You know, sometimes I look back and realize I made a major career error by leaving the Lisp community back in 1993 to do C++. That's the first thing that comes to mind. A more serious note, I mean, for the most part, the whole issue of the language that you use to implement your services is sort of entirely an orthogonal issue to the actual topic of the microservice architecture.
All right. Thanks, Chris. Our final question's an easy one. Where can people find your Lisp book?
Oh, that was actually not a book. That was in 1990 there was an issue of the CACM, Communications of the ACM magazine, that was all about Lisp. And I think I helped put that issue together, and I think I wrote an article in it. So if you go to portal.acm.org and search, you might be able to find it there.
Okay, great. Thanks.
Thanks for asking.
Let's get the link up on the screen just in case. What was that? Portal at or dot ATM?
Portal.acm, as in like Association of Computing Machinery .org.
Great. Let's put that up on the screen for folks. So that's where you can find the article.
Wow, that's all like right. 31-year-old memory. I feel old.
No, that's okay. No need to. Young at heart, always. All right. I think we are close to out of time. There's one last question. Would you like to take the time to answer it live?
Oh, yeah, sure.
Okay. And then we'll close it off here. Would you agree that a stacked monolith is a kind of anti-pattern?
Well, I assume by that you sort of mean one that's organized around technical layers like web, domain, and persistence. I wouldn't say that it's an anti-pattern. I mean, it just represents a particular set of trade-offs, and you know, and it works well if you're building something simple. But you know, once you scale, you start scaling up your code base, you could run into issues. So sure, you can use it for simple things, but you know, for the most part, if I was to build a monolith, I would probably build it with a modular architecture instead.
Okay. All right. Well, that is the final question we have. Thank you, Chris, so much for your time, and hope to see you soon.
Oh, yeah, this was fun.
Good.
Enjoyed it. Thank you.
Good. You're welcome. Enjoy the rest of your day.
Yeah, thanks. Bye.